Hi everyone, my name is Nurul Azhar Muhammad, and today I'm going to explain about energy density in electrostatic force. Energy density is defined as the total amount of energy stored in a system per unit volume. Now, let's look at the concept of energy density. Here, I have a charge, namely Q1. Consider the point charge Q1 is transferred from infinity to the position R1 in the system. We will get that the work done is zero, which means that there is no work needed to bring the charge since the system is empty. Now, when we bring another point charge, namely Q2, from infinity to the position R2 in the system, we will get that the work done is equal to Q2 V1. Then, another point charge Q3 is moved to the position R2. Work done is given as Q3 V31 plus Q3 V32. We can also write it as Q3 in bracket V31 plus V32. Thus, the total work done in assembling the three charges is given by W1 plus with W2 plus with W3. It's equal to 0 plus with Q2 V21 plus Q3 in bracket V31 plus V32. So we let this to be equation 1. Now, let's see if the charges is positioned in reverse order. The work done is given by the work done on Q3 to be moved to R3 is given as 0. Next, when a point Q3 is moved into the system at point R2, the work done is given as Q2 V23. Next, when the point Q1 is moved to the position R1, we will get that the work done is equal to Q3 V12 plus Q3 V13. It is also equal to Q3 in bracket V12 plus V13. So the total work done is given by VW3 plus with W2 plus with W1. It is also equal to 0 plus Q2 V23 plus Q3 V in bracket V12 plus V13. We name this as equation number 2. Next, if we combine the two equations, we will get that 2W is equal to Q1 V1 plus with Q2 V2 plus with Q3 V3. W, we will get it as half in bracket Q1 V1 plus Q2 V2 plus Q3 V3. We can also write it as half summation of K equal to 1 QK Vk. In system of continuous charge distribution, the total work done is given as follows. From Gauss' law, we know that Labla D is equal to rho V. Then, when we substitute that into the equation, we will get that work done is equal to half integral V Labla D V dV. Then, using the divergence theorem, we will solve the equation where we will get that the energy density is half epsilon naught E squared. Let's see an example of question regarding this topic. The question is, point charge Q1 is equal to 1 nanocoulomb, Q2 is equal to negative 2 nanocoulomb, Q3 is equal to 3 nanocoulomb, and Q4 is equal to negative 4 nanocoulomb are positioned one at a time and in that order at 0, 0, 0, 1, 0, 0, 0, 0, negative 1, and 0, 0, 1, respectively. Calculate the energy in the system after each charge is positioned. So the question wants us to find the work done of each charges after it was positioned in the system. So let's see the work done to move Q1 to R1. So work done is 0. It's because no work needed to move Q1 to the system as the system is empty. So work done for Q2 to be moved into the system at position 1, 0, 0 is given as Q2 V1. It is also equal to Q2 V2 divided by 4 pi epsilon naught magnitude to position 1, 0, 0 minus with 0, 0, 0. The answer we'll get is negative 18 nanojoule. Next, the work done to move Q3 into the system is given by work done 3 is equal to Q3 in bracket V31 plus V32 plus Q2 V21. When we substitute this into the equation, the final answer will get it as negative 29.18 nanojoule. When we look at the work done to move Q4 into the system, so it's given as Q4 in bracket V41 plus V42 plus V43 plus Q3 in bracket V31 plus V32 plus Q2 V21. Actually, when we look at the equation, Q3 in bracket V31 plus V32 plus Q2 V21 is actually work done to move point charge of Q3 into the system. So we can write it as W3. When we substitute that into the equation, the final answer will get it at negative 68.27 nanojoule. That's all from me today. Thank you.